Our next speaker is, thanks guys, our next speaker is Leddy from PM Group. And as you may be aware, PM Group is Ireland's largest A&E firm with more than 2,200 staff throughout the world. Con is responsible for PM Group's sustainable energy engineering services. And he was chairman also, he tells me, of the NSAI committee that developed the new Irish standard IS 399, Energy Efficient Design Management. And it's that he is going to talk to us about and share his insights on. Will you put your hands together, please, for Con?
Okay, thank you very much. Okay, first of all, the purpose of this new Irish standard was to establish a systematic approach to the design, construction and commissioning of new investment projects so as to minimise their energy use in their subsequent life. Now I'm going to start with a few examples. This is the Agio. And the Agio was one of the pilot projects for the processes in this particular standard. Now, what the Agio did was they took their baseline design and challenged it. And through that challenging process in the design phase, they've managed to reduce their energy consumption by a cumulative figure of 20% below the baseline case, a significant achievement. No silver bullet here. This is all a lot of small ideas, maybe some big ones, but principally small ideas. The next one is one of our own projects. Again, I don't have hard data on this, but we implemented the processes from the standard in this project. It was for GSK Biologicals in Belgium. One of the notable features of this project is that 75% of all of the building heating is recovered from a process waste. And finally, this is another project of ours, and I suppose this represents the lost opportunity in design. This was a benchmarking study that we conducted for the Singapore Ministry for the Environment and Water Resources. And what we established through that project was that there was up to 30% electrical saving opportunities possible within their existing industry profile, based on an average 4-year payback. Now, that is based on retrofitting good design solutions. Generally, by getting it right first time, we can actually minimize investment costs in our capital projects. Okay, so just about the standard itself, and I mean, we've defined energy efficient design as the organization, activities, guiding principles and control. Now, you notice here that I'm not mentioning anything about motors or best practices. This is about a management system. And you might say, well, why do we need a management system during the design phase to get energy efficient design? Surely our engineering companies are doing that already. Well, the answer to that is, well, why do we have management systems for safety, for quality? Unless we measure it and manage it, we don't control it. In safety, we now appoint a project supervisor for the design process. It's a critical appointment required by legislation. So what we're doing here is replicating what's happening on other aspects of the design to achieve best practice. Okay, this is just maybe how the system is broken down. This is a management standard. And the key part of this is the role of top management. Top management is responsible for the effectiveness of the standard. It is top management who makes the key appointments. It is top management who will set the objectives for the standard. They have a key role to play. They have a key role to play within design projects, and they also have a key role to play in terms of managing continual improvement. And these are the two different aspects of the standard. One is discrete project activities, but a key part, again, is the concept of continual improvement. It isn't good enough just simply to do the right thing within a project. We must learn lessons and feed it back into further projects. Okay, within the design project itself, we are recommending two key roles, new roles, if you will. The first is the idea of an EED owner. And that person should be within the investor team. That person should be independent of the investor's project team, and they should report to top management. That independence is very important, because what we don't want is energy efficiency to get sidelined through, let's say, pressures, particularly schedule pressures. All of these things typically will get sidelined because of schedule pressures. Then within the design team itself, we are recommending the appointment of an EED expert. Now, this person doesn't have to be a technical expert, as it were, on all aspects of the design. Rather, they have to be an expert in the process. Again, we're recommending, and it's important, that they have an independence from the design project team and that they report to the EED owner. So that's a little bit about the organization. Then some of the key processes. We've identified 2 key processes within the standard. The first is design for energy performance, and there are 3 stages in this. The first is where we do an energy balance study based on the concept design. In other words, we're preparing a baseline, and then we challenge it. And everybody in the team gets involved in this. This is a collaborative effort. We don't want engineering disciplines working in silos, and I'll give you a very good example of how that works. We collect the ideas in an energy saving register, and we sort them, we analyse the important ones, and then we decide what we will bring forward into the design. The implementation is also an important aspect of this, that we need to hand over these initiatives, particularly where there's a strong element of commissioning required or automation. Then we need to hand over all of these ideas correctly to the automation teams, to the commissioning teams. And of course, there needs to be a plan for verification. That's the first key process. The second one is what we call design for energy management. Now, it's in traditional design approach, energy management begins once the facility or the process is handed over to the end user. Typically, an energy manager or a facilities manager gets sight of it at that time. They've had no involvement in the design. They have their ideas as how they would like to manage energy, but the infrastructure is generally not in place to allow them to do it successfully. So what we're saying is that energy management, or operational energy management, should have a significant say in the design process, such that their requirements for energy management are captured in the design stage. We had a good example in GSK Biologicals, where the energy manager said to us, okay, when your systems prepare reports, I want chilled water broken down by process consumption and by building consumption. And initially the design team said, okay, that's easy. We'll just split the pipework coming out of the chiller room, and we'll have one system going to the process users and another going to the building users. But that made for an incredibly expensive piping design. But by careful analysis, we were able to look at the current design, and by simply changing from 2 meters to 4 energy meters, we managed to give him exactly what he wanted with little change in piping. So for a very, very small cost, the energy manager, the person who will be responsible for energy costs, energy management later in the operation phase of the project, was able to get exactly what he wanted. He could never get it if he was not involved in that design process. Okay, another key aspect of this is the idea of continual improvement. Typically what happens with projects is that we tend to work in isolation of each other. Even this happens within large multinationals. The lessons learned, the good ideas, what didn't go so well, doesn't get carried through. And that's what we want the continual improvement process to do, is to standardize successful EED initiatives. Another important aspect of this, and this is particularly relevant to the pharmaceutical industry, as part of the continual improvement system, we are encouraging companies to challenge corporate design standards. Corporate design standards are there to protect companies, to achieve a baseline in terms of design, particularly in terms of delivering quality. But their energy intensity implication is not understood. And what we're saying to corporates is, challenge your corporate standards. This must be done outside of the project life cycle. In many cases, we have seen where we've said to companies, look, your process for X, Y, and Z could be significantly improved. We've seen other companies doing it. This is how it should be done. And their answer will be, our corporate standards say we must do it this way. Within the confines of this design project, we do not have the responsibility or the authority to change that. So therefore, that's why these challenges must be done outside of the project life cycle. A final thing about this is the idea of investigating new technologies, again outside of the anger of a design project. Design projects are often nowadays schedule-driven. There isn't the opportunity to look at how we might implement new technologies. This should be done outside of the project life cycle in a continual improvement process. Okay, I've just taken this example here of, let's say, when does energy efficient design begin? And I've taken the example of clean rooms. The idea of looking at the process or the end user requirements should really begin before design. During design, we can really only look at the equipment or control. And post-design, we're into operation and management. Okay, another aspect that was developed through the energy management standard was the idea of looking at the energy service, the idea of looking at the layers of energy consumption. And the first layer we talk about is the energy service, the desired outcome that necessitates the consumption of energy. That's where the challenge must begin. What is the real need? So rather than defining it, let's say in a clean room as saying we need 40 air changes per hour, and a lighting system saying we need 500 lux, what's the task? What do we really need to achieve here? And then look at the process, and then look at the equipment. Okay, that's a summary of what I've just spoken about. Within the standard, we've also established what we term guiding principles for energy efficiency, and I'm only going to go through 2 of those with you. Very often we've seen companies saying, oh yeah, we want to be sustainable, so let's look at something like CHP or a biomass boiler or something like that. What we would say, no. Look at energy conservation and energy efficiency first. Exploit the opportunities that they will give you, and then look at renewable energy sources. The next one I have here, and this is just 2 of them, is exploit opportunities for energy recovery. For example, by configuring working temperatures of various processes to affect energy recovery. Now, you're not going to understand this, but now I'm not going to go through the detail. But this here is an example of the, it's just a description of the process that we use in GSK for energy recovery for the building heating. So typically, there are many streams within the process where waste heat has to be removed. And typically, that's done with cooling tower water. Likewise, on the other side, we need to heat the building, and typically, we would use steam or hot water for that purpose. Now, typically and traditionally, building heating systems have operated at, let's say, 82 degrees, 71 degrees Celsius return. And that has been driven by a requirement many, many years ago to avoid corrosion in oil-fired boilers. That requirement is long since gone, but that remains a design standard for building services engineers. We changed that, and we are operating the building heating system at 40-30. So at 30 degrees C return, we can now use that water to recover the waste heat from the process users. We have a facility in there that if the demand of the building is less than the process, we can remove the surplus through the cooling tower water. And conversely, if the demand of the building exceeds what's recovered, we can supplement it with steam. But the bottom line here is that for most 75% of the operational hours, 75% of the building heating is achieved from waste heat recovery from the process. Now, this requires building services engineers, utilities engineers, automation engineers, process engineers working in collaboration, not working as islands. So that's just some of the examples of how that standard would work. Thank you very much.